Hey everybody, going to be talking about mass and weight today. These are two words that are often used interchangeably. I can say I've got a mass of something or it weighs this much, but there actually is a difference. And now that we've been able to talk about gravity, I can get more into what the difference is and what you need to know about each one of these. So our objective today, learners should be able to show familiarity with the ideas of the mass of a body and its weight and be able to differentiate between the two. So, vocabulary words we're looking at, we're going to be talking about mass, matter, volume, and weight. We've already talked about volume quite a bit when we were measuring the volume of objects, and weight is kind of self-explanatory, but mass and matter are two concepts that we might have touched briefly on in other classes, but we really haven't engaged yet in this one. So the first thing we're going to talk about is mass. Mass is a measurement of how much matter a body has regardless of its volume. And matter is anything that occupies physical space. We are all made up of matter. You know, you are made of matter, your desk is made out of matter, your car is made of matter. Basically, if you can see it or touch it or smell it or any of those things, it is made of matter. Volume is the amount of space that an object occupies. So, for instance, a pile of bricks occupies a certain amount of space. A pile of feathers might occupy the same amount of space, but there's way less stuff involved because there's less matter in those feathers. So, your mass is the same on Earth as it is on the moon because when we're talking about mass, we're talking about how much matter is in your body. And that doesn't change if I put you on the moon, if I put you in the space station. It doesn't matter. You're still made up of the same amount of stuff. And so we call that mass. Now, weight is the force of gravity on your mass. So an object near or on Earth's surface has weight, and that's predictable because there's basically the same force of gravity pulling down on us anywhere that we are as long as we're inside of Earth's atmosphere. And that force of gravity is what we measure when we are measuring something's weight. So weight and mass, we might consider them to be the same as long as you're on Earth, but as soon as you step off of Earth, so example like my picture right here, as soon as this guy goes on the moon, he may have weighed 100 on Earth. He now only weighs 16.6 on the moon because the moon's gravity is very different. It's much weaker than ours. So weight is dependent on gravity, where mass is just how much stuff it's made out of. It's not dependent on gravity at all. So, taking a look at the actual equations, weight is equal to mass times gravity, which you guys can see down here. Weight is the force that's pulling you down. Or it's got a force, it's got an acceleration component that comes from gravity, and it has a mass component that comes from, well, however much stuff you're made of. And what we'll learn about next unit is that force is always measured in a unit called newtons. And we'll be driving that home a lot more next unit, as I talked about. So the Earth pulls on a force about 10 newtons on each kilogram of matter, or as I got more specific, it's actually 9.81 is actually the force that's being pulled down on you. So it's about 10. It's 9.81 newtons for each kilogram of matter. So you should be able to calculate your weight and your mass by figuring out the Earth's gravity and using those interchangeably. So if something weighs 100 kilograms on Earth, we know that there's about 10 newtons on each kilogram of matter. So there's about 1,000 newtons of force on that person. Now it's actually like I said, it's actually 9.81, so this answer could actually be more accurate at about 981 newtons per person. So that's the force of gravity that's pulling down on you. So the things that you guys need to know as a takeaway about these two things, and some extra things that you're going to want to have in your notes. Weight to mass, 1 pound is equal to about 0.45 kilograms. So 1 kilogram is actually equal to, like, I think it's 2.2 pounds. It's a little over 2 pounds. 1 pound is equal to 4.45 newtons. It's worth noting here that weight to weight newtons can be a unit for weight because weight involves the force of gravity. So if you're ever asked a question, and you probably will be, which of these is an appropriate unit for weight, we are looking at the newton as a unit of weight. So pounds is the imperial or English system version of this. We won't be using pounds as long as we can avoid it. We're really going to be looking at using kilograms for mass and newtons for weight. So for example, the SI weight of a person weighing 150 pounds, 150 pounds, there's your how many newtons there is for each pound. That's not per kilogram, that's per pound, is going to equal 667.5 newtons. So just a one that you can try out in your notes yourself. How much do you weigh in the SI system? I can't actually answer this because everybody has their own separate mass. But remember that your answer should be in newtons because newtons is our unit for weight. You always want to be focusing on doing this work in newtons. So just a quick reminder, I know we talked about this in class, but gravity is different no matter, or regardless of where you are, but usually we think about it as being different depending on what planet you're on. So for instance, on Earth, your mass is going to be 63.5 and your weight is going to be 623 newtons. On the moon, your mass hasn't changed, but your weight has certainly changed because there's less gravity on the moon. On Jupiter, your mass has stayed the same, but your weight is now significantly heavier. And then on the sun, it's just going to crush you to death. But once again, your mass hasn't actually changed. So mass stays constant regardless of where you are. Weight changes dependent on gravity. And that's all I have for you today. I'll see you in class.